So this is the last lecture for chapter 3. We're in section 3-3, and we're going to deal here with systems of particles. So now instead of having a single particle in our model, we're going to have multiple particles. And the question is how we deal with forces on systems of particles. Okay, so we'll just review Newton's laws for systems and apply it to a couple of examples. Um, the point that we're heading towards is that you can write F equals ma on a system and get accelerations of an entire system from the forces on that system, the external forces, and we'll see how that works in a minute. These days, people are modeling materials atomistically, that is, they're modeling forces between atoms within a material and studying the properties of the material as a result of those forces. And so that's kind of the ultimate example of studying Newton's laws for systems of particles. We'll just do a few particles now. This involves lots of particles. So let's look in a generic sense at an XYZ coordinate system with 4 particles in this case. One here, one here, one here, and one here. And we'll look at the forces not only externally on this system of 4 particles, but also the internal forces on each other, right? If we look at that material we just looked at, there are bonding forces between the atoms in a material, and those would be internal forces. And then these particles here would have a center of gravity. It's denoted here by G, and there's a position of that particle, RG, relative to the origin of the coordinate system. And we can study the motion of the system by studying the motion of that center of gravity. Okay, so capital F sub I is the total external force on particle I, and little fij is the internal force on particle I due to particle j. So this is particle I, this is j, this is 1, this is 2. Okay, so there's a Fij that's the force from J on I, and there's an Fji that's the force from I on J. And as we'll see later, those two are equal. So Fij equals Fji. That is, the force on I from J is the same as the force on J from I. And that'll come into play here. So we talk about internal forces, that is interparticle forces, and external forces such as gravity. The location of G, of the center of mass, is 1 over m times the sum over all particles of the particle mass times the location of that individual particle. And that's how you locate this center of mass. Okay, so let's look at Newton's law on a particle by particle basis. So we look at the first particle, the external force on particle 1, plus all the internal forces on particle 1 from the other particles. All right, and we're excluding, there's no force on particle 1 from itself, is the mass of particle 1 times acceleration of particle 1, right? So the acceleration of particle 1 is determined by the external force on 1 plus the sum of all the internal forces from the other particles within the system. And you repeat that all the way down for the n particles in our system, and it gives us n equations summing forces and finding accelerations on the n particles in our system. Okay, so then if we sum this over all the system, that is, we just add all those equations, then the sum of all the internal forces is the double sum of all the the sum of all the external forces is the double sum of all the internal forces plus the sum of all the products of the mass and acceleration. Okay, so this is the total external force. It's a vector, so that gives you a vector sum, which gives you the net total external force vector on the system. As I said, Fij has to be Fji, so all of these double sums cancel. This summation double sum goes to 0, and we're just left with this. Okay, now just to simplify that a little bit, the sum over all particles of a mass times acceleration is the second derivative of the mass times the position of the center of mass. Okay, so it's md squared r sub g dt squared, which we can write as the acceleration of the center of mass, ag. So it turns out that the sum of all the external forces is the mass times the acceleration of the center of mass. So the acceleration of the center mass of the system is the total mass of all the particles, uh, is the total force divided by the total mass. Okay. So that's the key to this working with a system of particles, is that the acceleration of the center of mass is um, determined by the sum of all the external forces, and you can ignore the internal forces when you're just looking at the acceleration of the center of mass. If you're looking at the acceleration of any individual particle within a system, you have to do all those internal forces. But if you're just looking at the acceleration of the center mass of the system as a whole, you don't need to worry about internal forces at all. Okay? So if the total external forces are zero, then the acceleration is zero and the velocity of the center mass is a constant. Okay, so this is a conservation of linear momentum. That is, no net forces means no change in total linear momentum. Okay, it doesn't mean the particles are moving at constant velocity. It just means the center mass is moving at the constant velocity. Okay, so let's look at some examples. First example is a woman or canoeist standing on a canoe. The canoe is just touching the dock, and now this person is going to walk to the other side of the dock of the canoe to get onto the dock. But it turns out as the person walks this way, they'll be applying forces back the other way on the canoe. The canoe will move back the other way. So the question is, when this person gets to the end of the canoe, how far is it from the dock? Because it will have moved. In the end, we'll assume the person weighs 175 pounds, the canoe weighs 33 pounds, and the length of the canoe is 10 feet. Actually, the distance the person will walk from one end to the other is 10 feet. And the question is, how far does the canoe move away from the dock during this process? Okay. So we draw a free body diagram of the system. The system consists of two particles, the person and the canoe. And the only external forces on this system are gravity on the person, gravity on the canoe, and then a buoyancy force on the canoe because it's in the water. All right. There's no horizontal forces in the horizontal direction, no external forces in the horizontal direction, so the velocity of the center of mass is conserved. So if we sum forces in the x direction, then 0 is the mass of the person times acceleration of the person plus the mass of the canoe times acceleration of the canoe. Okay, so there's no external forces. We have some kinematics. Accelerations are time derivatives of velocities. Okay. So we can integrate the force balance, right? We integrate those positions to get velocities. So the mass of the person times the velocity of the person in the x direction plus the mass of the boat times the velocity of the boat in the x direction is some constant. And that's just an integration constant. If we start at rest, then both the velocities are 0, and at rest we must have c1 equal to 0. So c1 is 0. So this is true right here for all time. Okay, we can integrate again to get positions. And so, sorry, up here we started with accelerations, got to velocities. Now we have velocities. We integrate again to get to positions. So we integrate this one, and we get mpxp plus mdxd is a new integration constant, c2. Okay, and we can find it by using the initial positions of the person. So for h equals 0, that is when we're just touching the boat. H is the gap here between the dock and the canoe. So we start at the beginning of our study with h equals 0. Then The person is a distance d plus L from the end of the tip of the boat. Okay, so MP times E plus L, and the boat is d plus L over 2. So the boat is MD times E plus L over 2, and that equals C2. Okay, so that's our second integration constant. We can put this in here, and we get our kinematic equation. So MPXP plus MDXD is all this. Okay. When P reaches the right end of the canoe, then XD relative to P is XD minus XP. So that is the difference between this distance and this distance. So it's this little gap here. And that's L over 2 when we just get to the end. So XD is XP plus L over 2 at the end of our analysis. So we can put that in up here and we get rid of XD and we can solve for XP. So it turns out XP is given by this. And so H is the distance from here to the tip of the canoe is about 8 feet. All right, so that's going to be a long jump. And I hope they have a row or something, an oar or something to help them get out. All right, so again, we're dimensionally correct. H is smaller than L, so that's good, and it looks pretty good. So just by understanding how to study a system of particles and conserving momentum, essentially, we've been able to determine the answer to that. One more problem is a pulley problem. So we have some mass A, which we're trying to lift. We attach some pulleys to it, and we apply a load at point P. P will go down, A will go up. Okay, and because of all these pulleys, then it requires less force here to move A. Okay. So how do you study this? The first thing we do is we take out these 3 blocks and write free body diagrams on those. So we have a block here, a block here, and a block here. The forces the forces on P are gravity and the tension in the rope. The forces on A are gravity and the tension in this rope. The forces on this block are gravity, this tension from here, and the tension in these 4 ropes. Now, we're going to assume these pulleys don't have any mass and that the rope has no stretch in it. Those things complicate matters, but if we do that, the tension in the rope is the same everywhere. Okay? So now we know the tension in the rope or can figure it out, and that'll help us solve the problem. So we draw free body diagrams on this, and on this. Okay, on body P, there's just weight down and 1 force up due to the tension. On body A, there's 1 weight down and 1 force up. Notice this tension is not the same as this, okay? Because it's not the same rope, it's a different rope. And then on this body, there's 4 tensions up, and those are the same as this because it's the same rope. There's weight down, and then there's this tension from this rope. Okay, now we can just sum forces on those bodies. So on body A, MAG is minus TH is MAAA. So the acceleration of body A, this one, depends on the tension in this rope and its weight. Okay, on body B, which is this one, there's 4 tensions up from this rope here. Okay, there's 1 tension down from that rope, and then there's the weight. So there's the weight, 4 tensions, 1 tension, and that gives us acceleration. And then in body P, there's just its weight and the 1 tension. All right. Kinematics, we assume the rope's not stretchable, so we let LG be 4YB, right? YB is this distance, so it's the length of this rope here, okay, plus YP, which is this length, right? So we have this length plus 4 of these gives us that. So 4AB plus AP is 0, all right? So that tells us if body P is accelerating, that tells us how body B will accelerate. And then the acceleration at point A is going to be the same as acceleration at point B, a body B, because this is assumed to be inextensible. So if this one's accelerating, this one's accelerating. So between these kinematics and these force balances, we can solve the problem. So there are 5 equations, 5 unknowns. We can solve for all those, and we get 2 accelerations, the tension in the one rope and the tension in the other rope. So notice that these are identical, these 2 accelerations, except the acceleration at point B is 4 times the other one. All right. So that's why you can get some advantage, some mechanical advantage from a pulley system like this. So everything's dimensionally correct. The accelerations are in opposite directions. Notice there's a minus sign right here and not one here. And the tension in TG is always positive, so the cable never goes slack. So that's basically how you deal with systems of particles.